Most people think their computer is a magical box of light and mirrors. It isn't. It's a rock we tricked into thinking by flattening it and drawing microscopic lines of lightning on it. That rock is the central processing unit, the CPU. At its core, a CPU is just a collection of billions of microscopic switches called transistors. These switches are either on or off, representing the binary states of 1 and 0. Everything you do scrolling through a feed, compiling a massive script, or rendering a 4K video is just a result of these switches flipping billions of times per second. This happens through the fetch-decode-execute cycle. The CPU fetches an instruction from the RAM, decodes what it's actually supposed to do, and then executes it using the arithmetic logic unit. It's a repetitive, mindless process that happens so fast it creates the illusion of intelligence. But the efficiency of this process depends entirely on the architecture. This is where the divide between the Apple Silicon M1 and the Intel i9 becomes a technical battlefield. Intel is based on the x86 architecture, specifically complex instruction set computing, or CISC. Think of an Intel i9 like a heavy-duty freight train. It's massive, it's powerful, and it can handle incredibly complex tasks in a single go. But a freight train is thirsty. It generates a massive amount of heat because those complex instructions require a lot of electrical pressure to process. Inghan Innovi. The goal is raw through. It pushes more voltage to hit higher clock speeds, which is why your laptop sounds like a jet engine taking off when you open more than 3 Chrome tabs. Intel's architecture is built on decades of legacy support, meaning it still carries the baggage of instructions designed for computers from the 1990s. It's powerful, but it's bloated. Apple's M1 and the Silicon series that followed uses ARM architecture, which stands for Reduced Instruction Set Computing, or RISC. If Intel is a freight train, the M1 is a fleet of high-speed electric motorcycles. Instead of trying to do complex things in one heavy step, it breaks every task down into tiny, simple, hyper-efficient instructions. Because the instructions are simpler, the CPU can execute them with significantly less power. This is the no-fluff reality of mobile computing. The more you simplify the instructions, the less heat you generate, and the longer your battery lasts. Then there is the physical layout, which is perhaps the M1's greatest trick. In a traditional Intel system, the motherboard is a modular city. You have the CPU in one neighborhood, the RAM sticks in another, and the GPU somewhere else, all connected by digital highways, called buses. The M1 uses a system-on-a-chip or SoC design. It puts the CPU, the GPU, and the memory all on the same piece of silicon. This is unified memory architecture. By putting the RAM right next to the processing cores, Apple eliminated the transit time for data. There's no more waiting for the bus. The data is already there, accessible at a bandwidth that traditional modular systems can't touch. We are currently fighting the laws of physics at the nanometer level. We are cramming billions of transistors into spaces so small that electrons start to behave weirdly. They leak through barriers they are unsupposed to cross, a phenomenon called quantum tunneling. This is why the war isn't about gigahertz anymore. It's about lithography and instruction efficiency. Intel fights this with sheer voltage and massive cooling solutions. Apple fights this by refactoring the physical layout of the machine itself. One is a brute force approach that works if you have the thermal overhead and a constant power source. The other is a triumph of integration and efficiency designed for the portable age. Neither is better in a vacuum. It depends on the instructions you're giving the machine. But as a developer, you need to realize that the code you write is ultimately just a request for electrons to move through these gates. Whether those gates are CISC or RISC determines if your code feels like it's flying or if it's dragging a freight train up a hill. The machine doesn't care about your intentions. It only cares about the efficiency of the gates. Understanding the silicon is the only way to truly master the stack. Everything else is just a distraction from the hardware reality.